CTA is an ambitious project to build the next generation of ground-based gamma ray telescopes, to build on the success of the current generation, HESS, MAGIC and VERITAS. I asked Professor Jim Hinton to tell me more about the CTA.
These experiments, VERITAS and MAGIC and HESS, reached a sort of breakthrough sensitivity where it was possible to make lots of interesting measurements, but they don't really have the sensitivity to solve the problems, you know what I mean? So they've raised lots of very interesting questions, but to really sort things out and fundamentally revise our understanding of the energy universe, we need something that's very much better. So, and the nice thing in our field is that there's sort of consensus amongst all the rival teams who are working on these current generation experiments to basically get together and build something big.
To make CTA much better, there will be 2 sites made up of an array of 3 different telescope sizes with over 100 telescopes overall. The different telescope sizes detect different gamma ray energies, and having so many improves the angular resolution and the number of gamma rays which we detect.
We're pushing in lots of different directions in terms of improving the instrument performance. So we have a wider field of view, we're much more sensitive, we can look at things further away, we can look on shorter timescales, collect more gamma rays. So everything is better, and we push, in particular of interest to me, we push to very, very high energies for the first time. So it's the frontier of the electromagnetic spectrum. We're really moving into a domain where we've absolutely no idea what the sky looks like, for example, at 100 TeV, and the CTA will find out, you know, what's out there.
The CTA will have 2 sites, one in the northern and one in the southern hemisphere. The southern hemisphere site will be able to look at both galactic and extragalactic objects, whereas the northern site will mostly look at extragalactic objects. And this is because of the orientation of the Earth with respect to the rest of the galaxy. So if we draw the Earth onto this galaxy, which looks much like our own galaxy does, the Milky Way, then what we can see is that the southern site points towards the galactic centre. So we'll be able to see plenty of galactic sources there, and we'll also be able to look outside our galaxy and see extragalactic objects too. Whereas the northern site will point out of the galaxy, and so we'll mostly be able to see extragalactic objects. Deciding where to build the telescopes is not easy. There are many different factors to consider. The sites must be very dark, away from the light pollution caused by cities, because gamma rays cause flashes of very faint blue light when they interact with the atmosphere, as explained in the Cherenkov radiation video. So the light from cities would drown out the faint flashes. However, the observatory must be close enough to civilization that it is easily accessible to scientists. The site should also have clear skies to maximise the number of nights when observations can be made. This has the added advantage of meaning that good wine is often made near to observatories. The site must be reasonably flat to make supporting the telescopes easier. High wind speeds are not ideal and can increase costs if the structures have to withstand them. The site should not be near potential earthquake sites for the same reason. Snow and ice are also not ideal because they cover the telescopes and prevent observations. The host country should also be politically stable.
So there's lots of factors to go in, so there's a lot of people working hard on that now. But we hope by the end of this year we'll be able to choose the sites.
Candidates for the northern sites are Baja, California in Mexico, 2 sites in the state of Arizona in the USA, Tenerife in the Canary Islands, 2 sites in the Indian Himalayas, and 1 site in western China. And candidates for the southern sites are a site in northern Chile, 2 sites in the west of Argentina, and 2 sites in Namibia. So we need to carefully consider where we put the telescopes. But how do they work? This is a schematic diagram of a simple telescope. The Cherenkov light is reflected off the telescope mirrors and into an array of detectors which make up the telescope camera. The signal is then analysed so the direction and energy of the original gamma ray are worked out. I asked Dr. Richard White to tell me more about the detectors that the telescope will use. These have to amplify the very faint signal from the Cherenkov light.
The detectors themselves have to be pretty sensitive. So you need to detect anywhere from a few, 1 or 2 photons to tens of photons.
Right.
So you need a detector that can see single photons. And the timescale of these Cherenkov flashes in the atmosphere is a few nanoseconds. So the detectors also have to be very fast. So this, for example, is a more traditional photosensor, a photomultiplier tube, taken from the Veritas Gamma Ray Observatory. And you can see this is around 1 inch across, and the camera consisted of 500 of these. For CTA, one of the options for the smaller telescopes is to build these things with dual mirrors as opposed to a single mirror. And in this case, we can use much more compact photosensors. So this again is a photomultiplier, but now in 2 inches across we have 64 individual channels. So each channel is 6 by 6 millimeters.
These are traditional photomultipliers, but the CTA could use a new type of photomultiplier made of silicon.
So this thing has a lot of advantages. So it is smaller, it's a lot more robust. These devices, these photomultipliers detect single photons, but if you expose them in daylight, they basically die straight away. They require 1200 volts to work. This device requires only 70 volts, so it's a lot safer. It's completely robust to daylight. And it doesn't involve vacuum technology, so they're easier to manufacture. They're printed in a similar way to microchips. So once you've decided on your design, and once it's proven, making more of them is reasonably cheap for the companies. There are some disadvantages though. I mean, performance-wise, the detection efficiency is higher, but they experience things like crosstalk and temperature sensitivity that we're trying to understand. So for the compact high-energy camera that we're working on here in Leicester, we'll be looking at building one camera with these and one camera with these, and those will both be ready on the timescale of 2015. And those will go into the first CTA prototype telescope, which we're building on Mount Etna with some Italian colleagues.
These telescopes will be prototypes so that any problems can be identified before the entire CTA array is built. I asked Jim when the CTA would be ready to make observations.
CTA, as I guess Richard was telling you, is in the end should have more than 100 individual telescopes, and it won't be finished probably until 2020 or something like that.
Right.
But we will be able to make observations as we go along. So in the partially constructed array, well, as soon as there's basically a few telescopes ready, it would already be the most sensitive instrument. But we hope that from about 2016 we'll be doing science with CTA, and then the instrument gradually from that point on get better and better.